Hi, this is Kevin Trainer, and I'd like to welcome you to my tutorial demo. This demo is a companion to my lecture on Chapter 4 from the Murach second edition MySQL book. Chapter 4 is called How to Retrieve Data from Two or More Tables, so that's what we're going to be doing. What I'd like to do in this demo is I would like to begin to explore the structure of the database that we're using for our exercises, the My Guitar Shop database. So I am going to show you an EERD, an extended entity relationship diagram that I created for the My Guitar Shop database. And I think this is an assignment you're going to do in chapter 10, chapter 11, something like that. And I've kind of jumped ahead and done it for you ahead of time, so you have something to check your work against when you get there. Entity relationship diagrams are a way for us to both design relational databases and to use. They're a tool that we can use as an aid while we're trying to use relational databases. Since this particular database is already designed, well then this is going to be sort of a job aid for us as we're working. Now, when we design relational databases, we go and look at our problem space, and we try to identify what the data entities are that are of interest in our problem space. And here, in this case, here are the entities that we identified. Customers, orders, order items, which I'll explain in a minute, products, categories, addresses, okay, and administrators. These, I think, are administrators for our application system. Okay? Now, so these are the things that interest us. So we made each of these an entity in the entity relationship model when we came up with the logical data model for our application. And then in a second step, when we turn this into a physical database, we turned each of these, I just want to mention that these rectangles with the rounded corners on this version of the diagram, these are the entities. And then the entities, when we move from a logical data model to a physical database, the entities become the relational tables. So the customer's entity becomes the customer table. The orders entity becomes the orders table, etc. So here we have one of these rounded rectangles for each one of our tables. Okay. And then we have lines in between them. These lines are relationships. And I think I talked you through one of these back on, the lecture for chapter 1. But the relationship between customers and, well, let's not talk about customers and addresses yet, because that's kind of a complicated relationship in this particular database. So let's look at the relationship between customers and orders. Okay. First of all, how do we read this line notation? Well, the existence of the line could be read as has a relationship with. So the customer's table has a relationship with the order's table. Okay, and these notations at each end of the line it describe these things that we call cardinalities. How many of one goes with how many of the other. And you read them like this. just sort of imagine yourself kind of standing on the customer's part of the diagram and looking across the orders. And you'd say, okay, one row in customers is associated with how many rows in orders where you read the cardinality notation at the opposite end of the line. So this says one to many. This crow's foot notation means many. And of course, the one line means one. And then look at it the other way. Stand on orders and look across the way at customers. And you say, for each order, it's associated with, and here's how you read this, one and only one customer. And when you think about the relationship between customers and orders, that's pretty much what we would like. So these relationships are implemented in relational databases with these foreign keys. Okay, so because this is a fully designed relational database, it already has the foreign keys in it. So if we're looking at something on order that's going to properly point to customers, well, it's going to point to its primary key that has a little key symbol there. And look, customer ID. And look, it has a little pink or salmon colored diamond next to it. And a lot of these foreign keys have that kind of notation in this diagrammer. The diagrammer that I use for this is MySQL Workbench. And I was able to import the database into the diagrammer and have it draw the diagram for me automatically, which was pretty easy to do. And of course, you're going to learn how to do that too. So we have a foreign key on orders that points over to customers. Is there a foreign key that points back? No, typically not. Okay? Typically, the foreign key on one side, the many side, see how we have the many over here, points to the one side. Well, why is that? Well, when you think about the way rows work, okay, if we want to point at a row, we can't point from the one side to many rows in the many side because we've only got one foreign key value to point. So how do we point? Well, we point from the many side. Now each of those rows is only associated with one row in the other table. So we point from the many side to the one side. All right. Okay, so that's how we do these things. So there's a relationship between orders and customers, and that is implemented by the customer ID on orders. So let's look at order items. Order items describes an order line. Okay, ideally we would like to sell more than one item per order. That's how you make a lot of money in a guitar shop. Is you don't let them buy just a guitar. You say, well, how about a keyboard with that? Or how about some drums with that? Or how about at least a set of guitar strings, right? So we need to have more than one item on an order, and we do that by, some people will call this entity or table order line. Some people will call it order items, and here they've called it order items. Okay? And then there's a relationship between products and order items. And the order items table is an interesting table because it is actually this thing we call an associative table. It connects two other tables and makes a many-to-many relationship possible. So it allows each product to be on many orders and each order to potentially have many products. And it's the nature of relational databases, and we're going to learn about this as we go, that they can't implement many-to-many relationships directly. They need these associative tables. So what this does is it holds two foreign keys. So it points back to the order ID. So there's a relationship between order item and order, and that's implemented with this foreign key order ID. And there is another foreign key that points at product. Okay. And actually, the primary key of order items is usually considered to be a combination of order ID and item ID. And I don't know why we don't have two key symbols here. Probably a bug in the diagrammer at this point. Okay. All right. So this is how we make these things go. Now, I just want to point out that these relationships are associated with these things we call foreign key constraints. Okay? And if we set up the foreign key constraints the right way, which I think they pretty much have with this particular database, it keeps us from getting from breaking the relationships. Okay, so for instance, every time we go to add an order, we have to provide the customer ID. If we don't, it's not going to allow us to add the order because there's a constraint that says each order must point to a customer that's already in the customer table. So if we were going to put a new order into the system, we'd have to add the customer first and then add the order. On the other hand, if we're working with the customers and we go to delete a customer, the server will look and say, well, is that customer in a relationship with any of these orders? And if it is, it's going to say, oh, no, you're going to have to do something to break the relationship between that customer and the orders that point to it, or we're not going to allow you to delete the customer. So this concept of keeping all the pointers between tables intact is called referential integrity. And what it's essentially doing is each of these relationships is based upon a foreign key constraint. And the foreign key constraint is what gives the server the information to maintain referential integrity. Okay, well that's enough of that stuff. Let's go explore some stuff. Okay, so I want to explore this database. So I'm gonna click and open a connection to it. And you can see I've got I've loaded the database, my guitar shop. Okay, and what I've done here is I've created a series of queries that I think will just kind of demonstrate the kind of things that we can do with this database. So I want to open them. The first one is pretty easy, invoices with customer name. Okay, so I've got, in the previous chapter, all of our queries were based upon just a single table. And in a properly designed relational database, that's not going to get you much information because of the fact that we have put all the columns on the entity that they relate to. If we want to have a useful query, we typically have to pull in columns from more than one table. Okay? So for instance, if I want a list of invoices, okay, I'm sorry, if I want a list of orders by customer, okay, how could I do that? Well, let's say the two tables that I need are orders and customers. Okay, I'm going to combine them with a join. All right, that's good. And what do I want? I want the last name, the first name, the order ID, and the order date. And I want this to come out in order of last name, first name, and order date. Good. Let's give this a run. And bring the answer up here. And as you can see, we have, if we look down in this action output log, we'll see we return 9 rows. Okay, so we have 9 orders. Okay, well that's good. And we joined orders and customers, so now we not only have the order ID and the order date, but we have the customer that's associated with it. And as you can see, one of our customer has more than one order. How about that? Alan Sherwood. Okay, well that makes sense. Now, you may remember from the lecture that only the rows that match come back. Okay? So for instance, what if we had an order that wasn't associated with a customer? Or what if we had a customer that wasn't associated with an order? Is that going to be a problem? Now, typically when I'm looking at this, I'm interested in maybe my current orders. So I don't have a problem if I have a customer that doesn't have an order. But if I have an order that doesn't have a customer, first of all, we've broken referential integrity on the database. Okay, so that's bad. And second of all, I have an order that I'm not showing. Well, how many orders are there? We got 9 rows here. Let's just go to the table and find orders and open up the data view. And we'll see there are 9 orders. Well, no, we got them all. Okay? Well, why did we get them all? Well, we got them all when you come back here because we didn't have to worry about not having a match, because the match between these two tables is maintained by the database when it's enforcing the foreign key constraint. Okay? So even though they have to match, we can rely on the fact that they're going to match because that's the nature of the integrity of the database because of the constraints that we set up when we designed it. Now, I don't know about you, but that allows me to breathe a little bit easier. Okay, well that's good. Let's look at the next query that I want to show you. Well, I didn't do anything very different here. I still have the join between orders and customers. But if we go back to the first one, I used the, I said on orders.customer ID equaled customers.customer ID. I had to prepend the names of the tables in this on clause, okay? Because they're from 2 different tables and I needed them to be unambiguously referred to. Now, sometimes people feel that that's a lot of typing, although in the case of a query this short, it's not. So let's go to this one here. What have we done? Well, we've used the table alias for each of the 2 tables. We've used O for orders, we've used C for customers, and now on the within the on clause I can say O.customer ID and C.customer ID. Now, I want to point out that if in fact you use the alias, okay, at least with our product, you have to use the alias in the on clause. So if we try to go back to having it be orders dot customer ID and we go to run it, we're going to get an error. Okay, because all of a sudden on this product, it doesn't recognize orders once we have aliased it when used in the on clause. Okay, so now I'm going to back up, change that, and run it again, and everything runs fine. So at least for the on clause, if we have used an alias, we had better use it instead of the table name in the on clause. Okay, table aliases in the on clause, pretty straightforward stuff. Let's look at the next thing I have to show you. Okay, the using clause. Okay, so here I've changed the query. The query's pretty much the same, except instead of having an on clause, because the field that we were matching on, the one that is the foreign key on orders and the primary key on customers, customer ID, because it has the same name on both of the tables, which is an excellent practice, we can just say using customer ID and remember to surround it with the parens. Okay? Well, how does that work? Works just fine. So we get the same thing. Now, I left the aliases in. I'm not really using them, but they don't hurt. Okay? Alrighty, let's look at some more stuff. Okay. What about we wanted to do a natural join? Okay, we've got it to join a couple of ways. We said use the on clause. We said on, and then we had field equal field. And then we said using, and then field. You can say natural join. Let's leave what that looks like. So if you do a natural join, you don't have to mention the fields. It's going to match them up by name. Okay, well, what are the fields, or what are the columns that match between these two tables? The only ones that match, there's only one column, and it's customer ID. So this turns out to do the same thing. Pretty nice. Okay. I think that natural is perhaps not a good practice. I mentioned this in the lecture because what if somebody adds another column to one of the two tables that causes more than one field to to match, and now we have a more restrictive query than we had before, and maybe we didn't really intend that. Okay, so I think that natural is an interesting idea, but perhaps could lead to bugs being introduced in your queries when your system gets into maintenance mode, which you probably don't want. Okay? All right, let's look at another thing. Okay, so before we do that, notice all along 9 rows return, 9 rows return, 9 rows return. Okay, there are 9 invoices, 9 orders in the order table, and we keep getting all 9. So everything's working fine. Okay, we're essentially getting one line in the result set per order, just what we wanted. All right. Now, let's look at this idea of a cross join, okay? So let's look at it with an explicit cross, okay? So instead of saying natural join, we say cross join. Now we're still going to get 9 rows in the answer set. No, we're not. Watch. How many rows do we get? Wow, we got 72 rows in the answer set. You can see that down here in the action log. 72 rows returned. Well, what is that? Well, that's what we call the Cartesian product of the two tables. That's every row on one table matched with every row on the other table. And I think we have 9 in. We have 9 rows in the order table and 8 rows in the customer table. So 9 times 8 is 72. Now there are times when looking at all the permutations of the combination of rows in two tables is just what you want. There aren't a lot of them, but there are times. Turns out that this is not one. Okay? So what we really want are 9 rows. We accidentally got 72. Okay? So someday we'll come upon a good application for a cross join, but we haven't found that. How else could we get a cross join? Well, it turns out we could get a cross join without even explicitly asking for it, even without putting cross in front of join. If we just say join, okay, and we've got no join on, we've got no conditions, then we're going to get a cross join. So let's run this. Whoops, 72 rows returned. Well, that's not anything that we want. We don't want any. What does it mean to be an exhaustive combination of all the customers and all the invoices? It's nonsense. Now, I just want to point out that here we have 8 rows and 7. Okay, just a few. What if you did that and you had 1,000 customers and 3,000 invoices? Well, you'd be waiting a long time for the query to come back. So one of the problems with cross joins, especially accidental ones, is you can be waiting a long time to get the attention of your server again, because they can bring back a tremendously high number of rows. What they bring back is what we call the Cartesian product of the two tables, which is usually not what we want. Occasionally, it's the answer we're looking for, but only occasionally. I just want to point out there's one more way to do this, and that is a cross join that comes from using the implicit join syntax. So if we don't say join at all, if we have no join word in the from clause, okay, and this is how we used to do joins before we implemented the standard called SQL 92, then we're going to get the join is going to be controlled by the where clause. Okay, that's the way we used to do it. That's called the implicit join syntax, and that's what I've said we don't want to do. And why don't we want to do it? Because if you accidentally forget the where clause, you get the Cartesian product. So let's look at how many rows we get back here. I have an error in my SQL syntax. Orders O, customers C. Well, how about that? And you know what? The alias feature is really part of the explicit join syntax. So let's get rid of these alias labels right here. Apparently I forgot to get rid of those. Okay, from orders join customers. Okay, so let's save that. and run it. And there we go, 72 rows returned. It would be nice if we were looking for that, but that's not a reasonable answer. We only have 9 orders, okay? 72 rows as a way to analyze orders is just things run amok. So what's interesting is we came up with a bunch of ways to get way too many rows, get the Cartesian product, okay? The current one is we're using the implicit join syntax, but we haven't remembered to add the where clause. Well, that's one of the reasons I don't want you to use the implicit join syntax. The one before, we're using explicit join syntax, but with no on or using clause, so there's no control over the join. And so again, we get the Cartesian product. And then the other one is we do a cross join, and we don't have any control over it, and we get a cross join is by definition the Cartesian product, and we get 72 rows back. So I'm going to say that unless you have a really interesting thought that you need 2 tables and you need every permutation of these 2, and you want to get the Cartesian product, you probably don't want to do any of the last 3 things that we've done. And if you get a result set back where you've got way too many rows, okay, you may look and go, did I accidentally get the Cartesian product? Okay, in which case you've made one of the mistakes that we've shown so far. All right, that's all those. Let's do some more exploring. So I'm going to go up and I'm going to close. Sorry, let's close them all. Let's go here and say we want to close them all. And I don't know how I managed to get this thing to move, but I do. I hit some combination of mouse keys and it does that. Okay, what else would I like to show you? Well, let's get down to number 2, invoice lines with customer name. Okay, so I'm going to join order items, orders, and customers. So let's go look at that in the chart. Order items, orders, customers. Okay, that's good. So I'm joining a little bit more than I was before. What I want to do is I not only want to have enough information to look at each order, but I want to know how many order items there are, because there are going to be some orders that have more than one item. Okay, well, let's see what that looks like. So we're going to shrink this. Okay, so we went last name, first name, order ID, order date, product ID, and quantity. Okay, so let's see how many of these things have more than one order item or order line. Okay, so first let's just run it. And we've got 12 rows returned. So that means to me that if we went from 9 lines to 12 lines, that means that probably 3 orders have another line. There are 3 more orders, 3 more lines than we would expect for 1 line per order. So let's look. So we've got order number 3 has got 2 lines. Order number 7 has got 2 lines. Oh, it's got 3 lines. 1, 2, 3. So 2 extra here and 1 extra there. That accounts for all the extra lines. So I can't emphasize enough how it makes sense to look at your result set, and you really want to be able to explain how you got the number of rows that you got. We have a row here for each order line. That's what we want. Okay, so that's just the number of rows we want in the answer set. And we have a good explanation of why that's happening. Okay, and how it's different from what we were getting from the previous query where we were getting one row per order. And we were getting 9. Now we're up to 12. We can explain it. Okay? All right, well, let's look at that query a little more, get rid of this part, a little more closely. So we joined order items to orders on the order ID field. And then we joined those things to customers on the customer ID field. Okay. That looks good. Now, when you look at this query, look at the results. It's kind of nice, but we don't even know the name of the product. We know it has a product ID 2, but we don't even know the product code or the product name. So that's not all that we want. What we really want to do is we really want to match across to yet another table and get some more descriptive information. So we're going to go from joining 3 tables here to the next one where we're going to join 4. Okay. So let's go here. So here we're joining one more. Okay. Now, because of the order that we were doing things before, I put the newest table on top. So I'm starting with products, I'm joining order items, I'm joining orders, I'm joining customers. Okay? And then what do they join on? Well, products and order items join on product ID. Okay? Order items and orders join on order ID. Orders and customers join on customer ID. And now, because we brought in that 4th table, we can look at the product code and the product name, which we weren't able to do before. So let's give it a run. Okay. So what's nice is that, okay, we still have 12 rows. Okay, we don't have any more rows. Okay, still got the 12 rows, but we've brought in 2 more columns that we were able to match to with the last of the joins that we have. So now we know that this first order line is for product code Les Paul, which is the product code for a Gibson Les Paul, a very nice guitar. Okay, and then on through there. Okay? Again, you'll remember that these joins, these normal joins, these inner joins, they only return the rows that match all the way across. And you will notice that we've been matching all the way across all along. We're not accidentally losing a row from the answer set because, for instance, we're not pointing to a proper row in the product table. And that's because if we go look at this, there's a relationship between order items and products that is maintained by the database management system. So this this foreign key that's on order items that points at product code, okay, this keeps us from creating an order item row that doesn't point at a proper product, or later on deleting a product that has an order item line pointing at it. Okay, so this referential integrity that is kept by having these constraints on the foreign keys means that we don't have to worry about the fact that we're doing these inner joins, because by definition we're going to have a match. Okay? If we have designed the database the right way and we have maintained it the right way, we're not going to drop rows in the answer set when we go from this one here, this query 02, which doesn't include the product table, and when we run that, we're getting 12 rows, and then we come along to number 3, which includes a product table, but we know that it's going to match because of the database constraints, and when we run it, not only do we get the columns, but we get 12 rows. Okay? So that's why that works. Pretty cool stuff. All right? All right, let's go a little bit farther here. Or further, actually, to tell you the truth. So what did we do? We did 03. Let's go to 04 and figure out what 04 does. Okay, so I want to point out, okay, that when we are just looking at the orders, we don't know the amount of the order. Now you might find this shocking, but let's look at the table. Okay, let's look at the table definition. Okay, what amounts have we got? We got ship amount, tax amount. Well, what about the amount of the whole order? Do we have a total amount? No, we don't. So one of the principles of these kind of relational databases, the ones that we design for online transaction processing systems like the one we have here, is that they're normalized. And that means we squeeze all the redundant information out of them. So that means that we don't typically carry a total order amount on the order table. If you want to know the order amount, you have to add up the amounts of the items. Now this really, to some people, it just makes them crazy. But we're going to say that if you kept the information both on order items and on orders, you could get them out of agreement with each other. Okay, and as soon as a database gets out of agreement, you get users who lose confidence in it. Plus, on top of that, we used to worry a lot about storage space, so we didn't want to use the space. So because of that, if you want to know the amount of an order, you have to be able to add up the items. Are we going to be able to do that today? No, we're not. Okay, because we're going to have to use some of the features from future chapters. But let's see if we can come up with the proper amount for each line. Okay, so what would that include? Well, it would be the we'd have the quantity times the item price less the discount. Now it turns out that I've looked at these, and the discount amount, it's an amount of money, it's not a percentage. So we take the item price less the discount amount and times the quantity, and then we get that. Okay? Now, let's look. So here we have, we've reformatted the query a bit so that we have line amount. So how do we calculate that? Well, it's item price minus the discount amount. That expression times the quantity is going to give us line amount. Let's see how much it is. Okay, and with things this small, you have to scroll a bit, but here we see this is the line amount for each one. Okay, and if you do this the right way, they sold 2 Les Pauls, which the good news is that those are big sales. The bad news is that they're selling them for not a lot of money. Okay, but line amount is the proper combination of all these things. So eventually, we're going to be able to calculate the amount of every invoice by taking the sum of the line amounts, and to do that we're going to have to learn the sum function, which we haven't done yet, coming in a future chapter, plus we're going to add the shipping cost, and I forget, what else do we have? The sales tax? Do we have sales tax? Yeah, the ship amount and the tax amount. So you have to have the total off of each order line. You have to sum all those plus add those other 2 things to get the total amount. Now, interestingly, if you're going to really start thinking like a programmer, you have to ask yourself what they're asking for. I think there's a couple of questions later in the book where they ask for the amount to be added up, but they don't ask for the shipping and the tax to be added in. So you have to really think, do they want the shipping and the tax on top of this or not? So, and that's just the question of what they're really asking for. Okay, so we've come a pretty long way. Let's go explore a couple more things. All right, so we're up to 04. Let's go up and let's take a look at my example of 05. Okay, so before I get into 05, I just want to say that at this point, we've fully explored the features of the chapter as they relate to normal joins, inner joins. Okay, I just want to remind you, in a normal inner join, you need to match all the way across the tables in order to get a line in the output. That's the bad news. Okay, the good news is you can set the constraints on the database such that you're always going to have a match when you need a match. Okay, so even though we were using normal old inner joins, we didn't seem to drop any lines because of broken referential integrity, because it was the nature of the constraints we had when we designed the database that the database server forced relational or referential integrity all the way along. So the next thing we're going to talk about are the other kind of joins, these outer joins. And the outer joins really only make sense when there's a possibility that we're not going to get a match across the tables. Okay? So what's an example where that's even possible? Because I've shown you a bunch of examples where the constraints that come from the database relationships won't allow us to get a situation where we don't have a match across the tables. Well, we do have some of those. So let's go explore 2 different ones. Okay? So I'm going to close these guys, and I'm going to open up number 5. Okay, now the relationship between customers and addresses in this database is a little odd. Okay, each customer can have each customer can have 2 addresses. They can have a shipping address and a billing address. Okay. Each address, the way that I set it up here, is associated with one customer, And they've got relationships going in both directions, which I think is a bad idea. So it's possible to add a customer without adding their addresses. Okay. It's not possible to add an address that's not for a customer. And again, this is a little flaky, but that's the way that they decided to design it. Okay. Now, knowing this, I want to know, are there any customers that don't have an address? Okay. Well, in order to do that, I have to be able to get a row into the output that hasn't matched on the address side. So how am I going to do this? Well, I'm going to join customers and addresses, okay? But I'm going to say for one of these columns that it doesn't have to match. And it turns out I want to see the customer even if it doesn't have an address. Why? But because I know from the experience I have with the schema for the database that it's impossible to have an address that doesn't have a customer, because that's the way they define the database. But it is possible to have a customer that doesn't have an address. And maybe I'm just looking at the integrity of the data in my system. So I use a left outer join. Okay. Now, why do we use a left outer join? Well, because the table that can fail and still appear with a row in the result set is the left one, the customers one. So I want a row for customers, even if I don't have a match on addresses. And because this is what I call a non-failing query, because the rows are going to go into the result set regardless, it's an outer join. So this is a left outer join. Let's run it. And how about that? A syntax error. Okay, now this is a classic case where what I did was to highlight some text. Okay, and I haven't highlighted a proper subset of the query that is possible to execute it on its own. So when I clicked on the left lightning bolt, it said, I can't execute that. Well, I didn't want to have anything highlighted. I want to execute all the lines in the query. So I unhighlight things and I run it. And here we are. And let's see, we got 12 rows returned. Okay. So we have 12 addresses. Okay. And I don't see, let me just pull down. I don't see, even though it's possible, I know, to have a customer without an address, I don't see that we have any. Okay, so we probably haven't gotten to the point where we have, come to the end of the year and we deleted all of last year's invoices, but we kept all the customers in case we sold to them again. No, we just, we've got a complete matchup between the two. But would it be possible to add a new customer and have it not have a proper address? Yeah, I'll show you that you can do that. So let's go to customers. I'm going to come all the way over to the right side. I'm going to click on the data layout. And you can see there are 8 customers. And I'm just going to add a new one, me. So let's say ktrainer@login.net. Okay, and I don't want to put in a properly encrypted password, but so I'll just put in the word secret for right now. And the first name I'll say is Kevin. And the last name is Trainer. And let's just see, do I have a shipping address? No, null. Do I have a billing address? No, null. Okay, let's apply that. Okay, so here it's saying it wants to insert into my guitar shop. Okay, fine, that's the insert. Let's apply it. Worked just fine. Okay, so let's rerun the query here. Yep, there I am. I'm customer number 9. So you would think if I go back to the other query, the one that has the left outer join, you'll be able to see that in fact I do have a customer that has no addresses. Let's see if that works. Yeah, we do. Look, trainer, Kevin, null, null, null. Okay, so I used an outer join here to explore the possibility of not having a match in the other table, because there are times, well, when you really think about this, you have to be able to add to one table before you add to the other. If they point to each other in a particularly sort of incestuous kind of way, you get to a chicken and egg kind of situation where you can't add to one table because you had to have to the other first and vice versa. So you typically can add to one, but then without being in the other, and then you have to you have a requirement the other way. So here we can add a customer without any addresses, but we can't add addresses without any customer. So how would we do this? Well, we would add a new customer, then we would go to add the addresses, then we would have customers with addresses. Now, is this a good design? No, I think it's a little flaky, but that's the way they did it. So here's a case where we used an outer join, and we were able to get matches. We were able to get a row in the answer set that did not match all the way across the tables, and that's we were really looking for. We were curious about the integrity of the data and how these two tables related to each other. Okay, so that was the nature of the question that we had. We used a left outer join. I've got to tell you, the first time I coded this, I said right. Why? I don't know. So if you're not getting the results that you want, you have to think a little bit closer, okay? Because it is the leftmost column that we want to be non-failing. We want to get the data out of the left table no matter what. Okay, and that's the nature of left outer join. Okay. All right. Now let's look at another outer join situation that I think you're going to find interesting as well. And this is, let's look at the relationship between products and orders. Okay. Now, again, you can't look at your diagram too much. I got to tell you. Okay. So let's look at, products and order items. Okay, so what I want to ask is, I wonder if there are any products that I don't have any orders for. Now, you should have that. I mean, some of your orders are going to be big sellers, right? And some of your orders, some of your products are going to be big sellers, and some of your products are going to be less so. Okay, so you could easily decide to carry a product in your store, and then there's a time when you don't have any orders for it. So we would expect to have some products for which we don't have any order lines. Let's go and see if we do. Okay, so we want to join products and order items, because our order lines are called order items, using product ID. This is a good case to use the using, okay? And what do we want to see? Well, we want to see the product name and the order ID, okay? And we want to have a left outer join. So if there are any products that are not associated with an order item, then we're going to see them. Okay? We wouldn't expect the opposite to be true. We would expect the database management system to keep you from having an order item row that points at a product that either wasn't ever there or is no longer there. But we could easily have a product that hasn't ever been sold. Let's run it. We do. We have this Hofner icon, which I'm not sure what it is. Perhaps it's a guitar. If I were a real rock enthusiast, I would know. And it has order ID null, which means it doesn't have any order lines. Okay? So for instance, Fender Stratocaster is on 2 order lines. Okay? Does anything else occur multiple times? Maybe. Let's look. Yeah. Washburn D10S is on 2 order lines. And the Hofner icon, it's not on any order lines at all. That's why we get the null. Pretty cool. Okay? So, again, how did I do that? Well, I made it a left outer join. Okay? Because the table on the left, products, is the one I want to be non-failing. Okay? I know that I might have products for which I might not have order items. So I put that on the left and I say left outer join. If I had it on the right, if I had it second, I just would put it second and make it a right outer join. There's no magic to that. Okay? It'll work either way. You just need to change the order of the tables and change it from left to right. Okay, so there you go. You're all set there. So this is a typical question that you want to answer with an outer join. Okay, there are some times when we expect that there may or may not be a match in the other table. Okay. Earlier, when we were using plain old mom and pop inner joins, we were pretty confident there was always going to be a match because it was forced by the referential integrity rules of the database. Here, not so much. I mean, it's a real question. Do we have products that haven't appeared on any order yet? And the answer is, yeah, we do, the Hofner icon. Okay, now the last technique that we illustrated in the chapter is a pretty cool technique that I like, where we use the union operator. And there just are times when we can't get all of the answer that we want from one select. So we have 2 or more selects connected with a union. A typical case, and the one that we keep showing you in the textbook, is when we want to classify rows in a table. Okay? So that's what I'm going to do next. Okay, so we're going to be looking at products. Okay? And what we want to do is we want to classify them as to how well they sell. Okay? How well they sell. I'm sorry. Okay? Now, if you take the query that we just did, where we did the left outer join with products and order items, we can change that query around a little bit and we can ask ourselves, what do we have that isn't moving at all? Okay, so the first select that we have here, it finds all the products that haven't sold at all, and it categorized them as a dust catcher. Okay, they sit on the shelves and they catch dust. Okay. Then the other thing we do is we take that query and we kind take that select and we kind of copy it, and we classify it the opposite way. Okay, this is a classification with only two categories. Okay, so something, according to this classification, is either a seller or a dust catcher. Now, this would be the kind of shop talk that you'd have. You'd say, that icon thing that we had. What was that called? Hofner icon. So somebody would say, "Oh, how about that Hofner icon?" And you would go, "Oh, that's a dust catcher. We've never sold one of those dogs. It just sits around and collects dust." Okay? Whereas, well, what is not a dust catcher? Well, something that sells. So here we've done one of the queries picks out all the rows that are not selling, all the products that are not selling. The other query picks out all the rows that are selling. The first query inserts a column dust catcher. The second one inserts a column seller. And when you put them together, because they only fall into two categories, each row is going to say either dust catcher or seller. Okay? And how did we get the second select? I just took the first one and turned it backwards. So the first one, I wanted to make sure that I got one that, first of all, I used the left outer join to make sure that I would get a row even if I didn't have a match with an order item. Then I had to come up with a where clause that would select that row that wasn't matched. And I just said where order ID is null. Okay? Then I just took the exact same thing, okay, and I put it down on the second query, and I said, I changed the categorization to seller from dust catcher, and then when it had said order ID is null, I said order ID is not null, it's the opposite. All right? And then I had to pretty up a couple of other things. One is I can't have a semicolon at the end of the first select because even though it's a select statement, it's a subpart of one big statement here that's union. So there's only a semicolon at the very end. Okay? And also, by the nature of the way these things work, you always put the order by on the last select in the union. So the order by is down at the bottom. So with those caveats, I'm going to run this. And look, everything's a seller except for the Hofner icon, which is a dust catcher. Well, we knew that before. We already understand that in the data. Okay, so understanding your tables. Oh, and how many rows did we get? Well, we got 10 rows. Okay, we got a row for every product. Okay, pretty cool. Very nice. So that's how we do this. I just want to point this out. So how could we make this a little more complex? If you wanted to use this same classification using union in order to have three categories, well then you would have you'd have another union between the second and the third selects. And then you'd have to have three categories, and then you'd have to have a way to differentiate them in the where clause to properly put them into three categories. Here is null and is not null. Well, pretty good stuff. Two easy categories. But you could take this kind of approach, not to these exact data, but to some similar ones. And you could categorize, you could put things into four categories. or 3 or 5 or 7 or 9, provided that you coded the query the right way. So this isn't the only use of union, but it's a very popular one, and it's the one that we're using so far in the book. And I'm going to wish you luck with it. So that's it. If you can do the queries that we've gone through here and you kind of understand the data like we have come to understand the data, you should do fine. You should be able to do all your exercises just fine. I'm going to put up a copy of the entity relationship diagram for my guitar shop with the chapter 4 exercises, so you'll have that to refer to for this and then for the future. And having said that, I'm going to say bye until next time. Bye-bye.